Okay, so there are a couple things that I kind of rushed over last time that I'd like to mention, and these are not that important, but they're kind of interesting, so I thought it'd be nice to show you. The first two are some details about complex multiplication. This is just a nice picture that I found in an old book by Conrad Knopp. Says, well, look, if you're thinking about multiplying two complex numbers, right? If you have, say, a complex number A and a complex number B, then one way of thinking of understanding the visualizing the multiplication is if you make a triangle from the point 1 to A and the origin, okay, right? And then you take that triangle and then make a similar triangle, right, where this length here becomes this thing here, right? And then you just make a similar triangle like that, right? So this is 1, right? And this length is going to be the product of the magnitudes then, right? So this length is going to be AB, right? And what you've done here is you've added on this angle to the argument of B, and so this is AB, right? So if you take this triangle here and then you make a similar triangle here, then that's AB, right? So that's kind of cute, right? And then going backwards, right? If I had a point B here, right, and I had a point A, right, and again I use the same triangle, but this time go backwards, right? So I start from here, right, and then go backwards like this, right? Then this point here is going to be divided by A, right? Because you've subtracted off the argument of A, and then you've divided by the magnitude of A, right? This is this is saying the same thing that we said last time, that when you multiply two complex numbers, what you do is you multiply the magnitudes and then you sum the arguments, right? But anyway, this is something I liked when I was young. Okay, so that's one thing about complex multiplication. The other thing is that you can embed the complex plane in the 2x2 matrices via the following map. So A plus BI gets mapped to A minus B, BA, right? So to this matrix, to this 2x2 matrix, right? So for example, right, I would get mapped to 0, -1, -1, 0. 1 would get mapped to just the identity matrix. So just a second. Again, a failed joke. Sumi was coming towards the door, and I pretended to close it in front of her, but she was like, "Oh no!" Yeah. Okay. Yeah, I should just give up. Okay. So, question. Yes.
You could also do this with the signs flipped on the b's, right?
I'm sorry?
You could also flip the signs on the b's, right?
Yes. Yes, it'll work out. Yes. Yeah. Yeah. Yes. Yes.
And then conjugation would be equivalent to transposition?
Yes, that's right. Okay. So so the thing to notice that if we call this map phi, then phi of z times phi of w is the same thing as phi of zw, right? If you work this out, right, like if you think about multiplication, right, a plus bi, c plus di, of course that's going to be right, ac minus bb, plus AD plus BDI, right? And if you take the corresponding matrices, right? Oops. Take the corresponding matrices, C negative D, D, DC, right? And multiply them. Well, you're going to get the matrix that corresponds to this, right? You're going to get AC minus BD, negative AD plus BD, right? AD plus BD, AC minus BD, right? So that's really nice, right? What that means is that this, and of course, addition is also, also preserved by this map, right? And so this is what's called a ring homomorphism, right? From this ring to that ring. Yes.
Should the coefficient of I be AD plus BC?
Oh yeah, thank you.
And the same in the, okay.
Sorry. Yeah. Yeah, same thing here. Yeah, thank you. Okay, right. Okay, so right, and okay, so you get this, you get this map from the complex numbers into the 2x2 matrices, very specific kinds of 2x2 matrices. And if you think about this a little bit, right, you can actually write this A minus B, BA as, right, we can factor out square root of A squared plus B squared, right, A over square root of A squared plus B squared, negative B over square root of A squared plus B squared, A over A squared, sorry, B over A squared plus B squared, A over A squared plus B squared, right? And you think about this, well, right, this is the cosine, right? This is the cosine of the angle, right? And this is the sine of the angle. So what you have here is cosine of the argument, sine, negative sine, cosine, right? And we can think of this thing as, as the magnitude times the identity matrix, if you want, right? And so what that is saying that, well, as you expected, as you know all along, that a complex number can be represented as a rotation and a scaling, right? That's exactly what we were saying. That's exactly what we said last time in a different way, right? So, yeah. So like, yeah. Scaling plus a rotation. Okay, so yeah, so those are two things that I kind of like. I think I was a bit insane last time, and it was just trying to rush. I had this because I have the improbable schedule in mind. I was thinking I should try to stick to that improbable schedule, but I think I should just admit that it's not going to happen. Okay, okay, so that's nice. Another thing that I actually said wrong last time was sequential compactness. Right. So sequential compactness is this business of whenever you have a sequence, there's a convergent subsequence. Okay, right, and that is in the case of metric spaces. Equivalent to just plain old compactness, right? The open covering, every open covering has a finite subcovering, right? It's also equivalent to limit point compactness, and this is what I said wrong last time. So limit point compactness is this business of whenever you have an infinite set, then there's a limit point in that. You're guaranteed a limit point in the ambient space. Okay. So in the case of metric spaces, all these things are equivalent. Okay, so just keep that in mind. You may have to use one or the other interpretation whenever we get to it. Okay. Okay. So okay. So just a couple. Now we sort of get back to the review. I'm not going to cover everything. So first, first thing that we're going to talk about is this thing called a region. So a lot of the theorems that we're going to deal with are defined on regions. So a region is simply we call omega a region, right? So it's called a region if it is open and connected. Okay, so any open connected set is called a region. Okay, we'll be doing a lot of theorems on regions. Okay, so I'm going to assume that you know what connected means. That should have been in your background. A theorem that a definition that you might not have seen is so-called path connected. So omega is called path connected. If for every pair of points in the set, you can create a continuous curve, gamma, into the set that starts at one point and ends at the other point. Right? So, oops, gamma of 0 is A, gamma of 1 is B. Okay, so it's just what you would expect from the name, right? You have a set, and no matter what pair of points you choose, you're always able to find a continuous curve that starts at one point and ends to the other point. So every pair of points can be connected via a path. It's called path connected. Okay, and I think this is an exercise. This is one of the homework exercises that if your set is open, then being connected is equivalent to being path connected. Okay, so okay, so other terms that you should know, ideas of convergence, right? Like, what does it mean for a sequence to be convergent? So convergent sequence. I won't insult you by asking you to tell me what it is. Let me just remark that if you've got a sequence of complex numbers, then the sequence converges if and only if its real parts converge, if it and its imaginary parts converge, right? So you can look at to check the convergence of a complex sequence, you just check the convergence of the component sequences. So so this is convergent if and only if the real parts, right? So let's say right, Zn converges to Z if and only if the real part of Zn converges to the real part of Z, the imaginary part of Zn converges to the imaginary part of Z. Okay, so yeah, other things that you're going to hope, if you don't remember these, please review your knowledge. You should know what a Cauchy sequence is. You should know that that Euclidean space with a normal metric is complete, right? And so C is also complete. Complex numbers are also complete. Okay. Okay. So other things you should know what continuity means, right? What continuity at a point, right? So continuity, right? What does it mean for a function to be continuous at a point, right? That like the the typical epsilon delta definition, and it's an exercise to see that this is equivalent to saying that, I'll just do it. So, yeah. So, right, being continuous at a point is the same thing as saying that the limit of f of z as z approaches z naught is f of z naught. Right. That's basically like a tautology. Right. That's the same thing as the same definition as the epsilon delta definition here. Okay. But it's an exercise to see that that being continuous at a point is equivalent to the fact that for every sequence that converges to z naught, f of zn converges to f of z naught. Yes?
Me?
Yeah.
Why is that different from the limit thing that you wrote earlier? Because I thought like the limit can converge to z0 as any sequence zn. Yeah.
So I guess one way is trivial, and then the other way requires a little bit of argument.
Okay.
Yeah.
Okay.
Yeah. So it's definitely true. Like if you have this, then whenever you have a sequence that converges, then this is going to happen. I'm sorry. Whenever you have a sequence that goes to z naught, then this is gonna happen. But to show the opposite direction requires a little bit of just a tiny bit of argument.
Okay. Because I thought what the top right was saying is that like limit as z goes to z0 means if you pick any sequence of z's.
No. So when I say like the limit of f of z as z goes to z naught is f of z naught, what I mean is really the epsilon delta thing.
Oh,
right?
okay.
Given any epsilon neighborhood of, given any epsilon greater than 0, right? There exists a delta greater than 0 such that if the distance from z to z naught is less than delta, then the distance of f of z from f of z naught is less than epsilon. Yeah,
Oh,
that's what I mean by limit.
Okay.
Yeah. So it doesn't mean like every sequence. Yeah, it's equivalent to that. So.
Right. Thank you.
Nope. You're welcome. Okay. Okay. Right. So that's continuity at a point, right? F continuous on a set, of course, means continuous at every point in the set, right? And one thing that I hope you recall is that if you have a function that's a function on a metric space is continuous if and only if the pre-image of every open set is open. Right. So for every E open in the domain in the range, excuse me. The pre-image of the pre-image of an open set is an open set, right? So this is another way of looking at continuity. It's sometimes called the topological definition. So it's equivalent to being continuous at every point. Okay, so hopefully you've seen that. Okay. So like this condition is what people use to define continuity when you don't have a metric, right? If you just have a space with a topology on it, how do you define continuity? Well, this is what one takes as the definition, right? Because you don't have a metric. Okay. Yeah. And if you haven't seen it, just try and work it out. It's not hard. Okay. Okay. Other things that we're gonna need. So continuity and compactness. So one thing that we're going to need is the extreme value theorem, right? So this is your old friend from calculus that says that whenever you have a compact metric space, whenever you have a compact metric space and a function going from that space into the reals, then that function is guaranteed to attain its max, and it's guaranteed to attain its min, right? So it's not, it's a generalization of your friend from calculus. Right? So f attains a maximum value. In x, and also a minimum. Right, so that's one thing we're going to need. Another thing we're going to need is that continuity on a compact set guarantees uniform continuity. Right. So if you're continuous on a compact set, then you're uniformly continuous. Right. So. Do people remember what uniform continuity means? Anybody want to tell me what uniform continuity means? Right. So you've got some function going from one space to another space. Right. Uniform continuity. So say f is uniformly continuous. What does that mean? Take a few seconds and write something down. Okay, that's enough. Somebody tell me what uniform continuity is. Anybody want to say? Right? It means that your continuity is uniform. Right? That's not a good answer. Somebody give me a real answer. Jaden.
Whereas for regular continuity, you can choose a different delta at every point.
Yes.
For the epsilon, you choose for uniform continuity, you have to have a delta that works for every point.
Exactly. Right? The delta works everywhere. The delta is independent of the point. Right? So so regular continuity is given a epsilon, there exists a delta such that so regular continuity at a point means that there's a delta such that that delta is going to work around that point, right? Everybody in the delta neighborhood of that point will be mapped into the epsilon neighborhood of the image, right? But in this case, it's that given any epsilon, there exists a delta such that if the distance between any 2 points is less than delta, then the distance between the images is smaller than epsilon, right? In other words, that delta works, right? So no matter what pair of points you chose. Okay. So we're going to need that. Okay, and here is something that I think we're going to need, which we'll call the distance lemma. So basically it says the following, that whenever you have a compact set, so K a compact set, and F closed set, such that K intersect F is empty. Then, roughly speaking, there exists a positive distance between the two sets. Okay, so that is, there is some definite distance. You can find like some definite distance between the two sets can't get arbitrarily close to each other, right? There's going to be some distance that the two points from each set can't be smaller, can't be closer than that distance. Okay. So the picture is like this, right? You have some compact set, right? And then you have some closed set, right? So you have some closed set like this, say. So the closed set is on the outside here, including the boundary, right? And what this is saying is that there's going to be some sort of like distance between k and f. Okay. So let's prove that. So, or do you guys want to try and prove it? Take a few minutes and see how you would start this off. Okay, just like how would you prove something like this? I'm gonna go outside and just wander around.
So suppose this is component distance, so that means you can pick any epsilon for that, like positive epsilon. And for that epsilon, you pick some k in case some f such that the distance equivalent is less than epsilon. Yeah. Okay. I think the point is that there's going to be a limit point of flow, right? There's a like that.
Yeah.
Yeah, talk to a neighbor. Maybe. Talk to a neighbor.
I guess it's just like.
And this comes and
There's
supposed, and their
like-
intersection is
We
empty.
do it by contradiction.
Like
and
some
it's just
like
that there's no
Yes.
positive distance, so that means
like
that
how
there
like
is-
distance
Yeah.
and then
That
like
means the same
since
point,
both
which means the intersection
Yeah.
is that is a moving contradiction.
just that.
Yeah, that makes sense.
And then you can contradict the k intersection.
It's a can arbitrary close to each
And it's
other.
like it.
This is a
I don't know.
Oh, yeah.
If that's like the
Intersection
best way to do
matrix.
it, right?
Intersection.
Yeah.
Yeah. That makes sense.
But
Okay. This maybe I'll just say how to do it. Unless somebody would like to say how to do it. Does somebody have an idea that they want to throw out, or if not? If not, I'll just show how one might do it. So you say, well, look, right? So FC is open, right? Right. The complement of F is open, right? And K is sitting inside of it, right? So you know that every point in K is interior to F complement, right? So you say, well, look, any point, right? Any K in K is interior to FC, right? Because K is inside of FC, right? So you say, okay, well, look, then every point here can be covered. Every point here can be given a neighborhood that doesn't intersect F, right? So for every point K, right, we know that there's some radius delta K that neighborhood of radius delta K doesn't intersect F, right? And then you play the normal trick. You cover everything with those guys, and then you get a finite subcollection, right? And then you take the minimum of the radii that are left, okay, and then take half of that, okay, and that radii will do it for you. That radius will do it for you. So let me lay it out. So like you say, well, cover K with things of the form, right? Neighborhood delta K centered at K, right, over 2, say. Right. Then there exists, by compactness, there exists k1 through kn, delta k1, right, a finite subcover. Your finite subcover. So then you say, well, let rho be the minimum of all those half radii. Right? Let rho be the minimum of all this half radii, right? So you've covered everybody with a half radius, right? You say, well, look, if you have some point P that's in K, then it's got to lie in one of these. It's got to lie in one of these neighborhoods, right? Then P lies in some one of these neighborhoods, right? Right. And then you think about the distance of P to F. The distance of Ki to F, well, that's controlled by the distance of Ki to P plus the distance of P to F, right? By the triangle inequality, right? And so the distance of P to F is bounded below by the distance of Ki P minus the distance of Ki to F. Right? Oh, I got it backwards. K to F, that would be very strange, minus the distance of Ki to P. Right? But you think about it, right? So like, if this is the distance of Ki to F, and this is the distance of Ki to P, well, the distance of Ki to P is smaller than this delta. Is smaller than this delta Ki over 2, right? Right, because we're inside that neighborhood, right? And the distance of Ki to F, the distance of Ki to F is larger than delta Ki, right? Right. Distance of Ki to F is larger than that radius, right? Larger than that radius, and so the difference between these two external numbers is going to be bigger than the distance between these two internal numbers, right? So that's bigger than the distance delta Ki minus delta Ki over 2, right? Which is of course 1/2 delta Ki, right? But that is bigger than rho. Right, because rho is the minimum of them. Okay. Right, and so you see that there, if you take that minimum of the half radii, then that basically gives you this this kind of fattening that stays away from F. Okay, so this I think this will be handy in what follows. I'm not sure, but it'll probably be handy in what follows. Any questions? Yeah.
Is there a proof you can do with limit points where you say they have to have a shared limit point?
They have
It's
to have
probably
a
not as nice, but
they have to have a shared limit point. K and F have to have a shared.
if they don't have a positive distance between them, they'd have to have a shared limit point.
Oh, I wonder. I don't know offhand. Maybe. Yeah, I don't know offhand. But as you say, this is a little bit nicer. Okay, so now we're finally going to do some complex analysis. So after all that okay, so let's start talking. Let's start doing holomorphic functions. So definition of holomorphic function is not surprising, not even maybe seemingly non-interesting, right? So you have some open set omega inside of C. You have a function, complex value function on omega, and you have some point z naught inside omega, right? So it's like the setting here, right? And of course, if the limit as the complex variable h goes to 0 of z naught plus h minus f of z naught over h exists, right? Or of course, the limit of f of z minus f of z naught over z minus z naught as z goes to z naught exists, right? Then we say f is holomorphic at z naught. Okay, so it's just what you know from from calculus, right? It's the same definition, except that we're using complex numbers now. Okay, and that turns out to be completely different. Okay, so in case you look at other books, holomorphic is sometimes called analytic. It's also sometimes called complex differentiable, or just plain old differentiable, or sometimes it's called regular. Okay. I think that's all I know for terms that mean holomorphic. But I remember being kind of confused looking at books and what is this? Yes, same.
So if we take a holomorphic function and restrict its domain to the reals, will it be analytic?
Yes.
Okay.
Yes. 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 Okay. 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 So Remark. Of course, this we define. F prime is at z naught is defined to be that limit, right? Right, and then f prime is called the derivative, et cetera, et cetera. Okay. So okay, so some other related definitions, right? So this is holomorphic at a point, as you expect, right? Holomorphic, you can talk about like holomorphic on an open set, right? That just means that you're holomorphic at every point in that open set. Okay. So as you would expect. But holomorphic on a closed set means that that you're holomorphic on an open set containing that closed set. Okay, so so it's not the same sort of thing. Okay, and third definition that Stein throws in here is entire, which simply means holomorphic on all of C. Okay, so later on we'll talk about entire functions. Okay, so some easy examples, right? You can just use the same calculations that you did back in calculus to see that if your function f of z is z, then f prime is going to be 1, right? That if f of z is 1 over z, then f prime of z is going to be negative 1 over z squared, right? The same calculation holds, okay? Right, it's the same sort of thing. But to give some non-examples, right? If we look at f of z equals z bar, then that's actually not is not holomorphic. Right? Because if you look at the limit of f of z plus h minus f of z over h as h goes to 0, right? Well, you're going to get right. You're going to get z. Sorry. You're going to get z bar plus h bar minus z bar over h, right? In other words, the limit of h bar over h as h goes to 0, right? Right? And if you're letting h approach 0 along the real axis, well, then that's going to be 1, right? But if you let h approach 0 along the imaginary axis, that's going to be -1, right? So, right, so so the limit doesn't exist, right? So, which doesn't exist, right? Or to give another example, so another non-example, if f of x is, say, z bar, right, then we look at this quotient again, okay, and we're going to get, you know, z bar plus zh bar plus z bar h plus h bar minus z bar, right, over h as h goes to 0, right? And these things cancel off, of course, right? And you're left with z bar plus h bar plus z h bar over h, right? And right, again, if you let right, again, if you let h go to 0, if you let h go to 0 on the real axis, you're going to get z bar plus z, right? And if you let h go to 0 along the imaginary axis, you're going to get z bar minus z, right? And so the only place that that's going to work out, right? The only place that that's going to work out is at when z equals 0, right? Because you're going to get 2z equals 0, so z would have to be 0. So will only work out at z equals 0. So this function, right? This function is you know, holomorphic only at the origin. Okay. Okay, everybody all right so far? Nothing amazing. Okay, so alternate perspective. So another way of thinking about holomorphic at Z naught is to realize that it's the same thing as saying that there exists some number, a complex number, f prime Z naught, such that f of Z naught plus h minus f of Z naught minus f prime Z naught h is h times some function phi of h, such that the limit of phi of h as h goes to 0 is 0. Okay. So I haven't done anything I haven't done anything different at all. This is basically just you take the definition of you take the definition right, that the limit is 0, and then just call this thing phi of h, right? And what we're saying is that phi of h being this guy, right? Let phi of h be this thing, and to be differentiable means that that this thing is going to.
You'd have to
I'm
subtract
sorry.
off the derivative.
Sorry, I'm a little bit off, right? Yeah, sorry. Yeah, so I need to subtract off this thing, sorry. Yeah. So let phi of h be this, thank you. Right, and what we're saying is that that the limit of this is 0. Okay, and if you just rearrange things, then you get this perspective. Okay, is everybody all right with that? Okay, good. Right. So what this is saying is that that your function basically behaves like a tangent line, right? Right. Back in real, let me. You could write it like this. F of z equals f of z naught plus f prime z naught, z minus z naught, plus some function of z times z minus z naught, where this thing goes to 0 as z goes to z naught. As z goes to z naught. Right? So if you think about it this way, it's very clear that what differentiability means is that your function behaves like a line, right? Your function behaves like the tangent, the linearization of your function, plus some error that vanishes quickly. Okay, so that's what differentiability means, and this perspective is going to be the one that's useful to us. I think will be very useful to us in improving things. So hopefully you saw this something like this when you did analysis in the reals. Okay, so it's from this formulation you can get immediately. Well, I mean, you don't actually need this for everything, but you can, from the definition, you can get the product rule, the quotient rule, and the chain rule. In particular, the chain rule follows immediately from thinking in this last way. So, yeah. So that's. Okay. So so holomorphic functions. Okay. So right. So right. So you see that the definition of holomorphic function is pretty similar to that of a plain old real differentiable function, but it's not the same thing as real differentiable, right? So if you're thinking if you think of this function, right? So this is a function from C into R, right? Because you're taking the modulus squared here, right? You could think of this function as a map from R2, right? So this is map xy goes to x squared plus y squared, right? That's a very differentiable function, but it's not a holomorphic. It's doesn't seen as a complex function. It's not a holomorphic function, right? So being real differentiable and being complex differentiable are actually quite different. And the thing that makes that difference clear is the so-called Cauchy Riemann equations. So Cauchy Riemann equations. Okay. So here it is. You have some function f of z, and let's write it as, let's give it this other way of expressing it as v of x u of xy plus I v of xy. If f is holomorphic, at some point z naught being x naught plus iy naught, then it turns out that u of x, the partial of u with respect to x is the partial of v with respect to y. The partial of u with respect to y is negative the partial of v with respect to x. Okay, so it has to satisfy right. It has to satisfy this. Okay, so okay. The proof of this is very simple. All you do is look at the derivative, and you let the difference go to 0 along the imaginary axes and the real axes, and you set them equal to each other, and then out pops the Cauchy Riemann equations. Okay, so let me sort of sketch that out. Right, f prime is going to be the limit of f of z naught plus h minus f of z naught over h as h goes to 0. Right. Let h be real. Okay. So I'm going to write this then as you have to. Okay. So I'm going to write this as x x naught plus h comma y naught plus iv x naught plus h comma y naught minus u of x naught y naught minus iv of x naught y naught. Right, everything over h. Right, and you see that right. So keeping h as a real variable here, right? What you get is, of course, the partial of u with respect to x evaluated to x naught y naught, and then plus I times the partial of v with respect to x and x naught y naught. Right. Now, if you let h be purely imaginary, so let h be, let me say it this way. So let h be real, and I'm going to approach along the imaginary. I'm going to approach along the imaginary axis. Okay. So along the imaginary axis, what do we get? Well, we get the limit as h goes to 0 of u x naught y naught plus h minus iv x naught y naught plus h minus u x naught y naught minus iv x naught y naught. Right. Everything over the change, but the change is IH, right? The change is IH, right? Because we're moving along the imaginary axis. Okay. And so what we get this time is right, the partial of u with respect to y. So we get 1 over I times the partial of u with respect to y, plus I times the partial of v with respect to y. So why not? Right. And so we get right. In other words, we get uv dy plus 1 over I du dy. Right. In other words, minus I du dy. dv dy minus I du dy. Right. And then right, setting the real parts equal to each other gives us that partial v with respect to x is partial v with respect to y, and partial setting the imaginary parts gives us that Vx is equal to negative u sub y. Are you okay? Is this, maybe it's not so interesting? It's not so interesting. Yeah. Okay. Yes, JN.
I may have missed it, but could you reiterate the purpose of the IH on the bottom?
Well, so we're letting we're taking. So we're letting this this change approach 0, but the change is going to go to 0 along the imaginary axis, right? So maybe I should write it like this. Is that helpful? Yeah. Yeah, we're letting IH go to 0, right? And so we've added on the change here. When we add on that IH, it affects the second variable, right? The IH affects the second variable. The IH is here. Maybe it's clear. Okay. Okay. So yeah. So that's one way of writing the Cauchy Riemann equations. Notice that. We could just as well have written this as the partial of f with respect to x equals 1 over I partial of f with respect to y, right? Because that's exactly what we're doing here, right? We're taking when we take when we're doing this, we're taking the partial with respect to x of your function, and then when we're doing anyway, this is the same thing. This is the same thing. Okay. Okay. So some simple examples, right? So like if we look at f of z equals z, right? That is to say x plus iy, right? And we take the partial with respect to x. Partial with respect to x is the partial of. So this is your u, right? And this is your v, right? And you see that the partial with respect to x